Hello, Dr. Anna and Professor Vivian. How are you? This is the second part of our video. I am planning to make 5 videos for 5 analysis. Just to revise what we did last video, we discussed about classical model analysis, and before classical model analysis, basically this is a video. You can find the link in my YouTube channel. I try to do a deep explanation about classical model analysis and why this research is unique and novel work. So for that, I try to make a literature review as well. Just to recap, let me open what we did last time. This is the model buildings. Linear and nonlinear model buildings are in our research. This is what I consider. Even last video I tried to show the modeling part, and we perform on these two non-linear models, classical model analysis, and we try to find the natural periods and frequencies of our buildings, and we check the health of the building as well. So in this research, this is a seismic analysis procedure. I try to explain also what type of procedures are there and which one is included. As I told you, linear static procedure, equivalent static analysis procedure. This is by default. We are considering, when we consider the static load cases, dead load, live loads, automatically we are using this one, linear static procedure, equivalent static analysis. Nonlinear static procedure, this is pushover analysis, capacity spectrum method and displacement coefficient methods, and both of them will be included in our research. So in the fourth part of my video, I will explain in depth what this means. Linear dynamic procedure, response spectrum analysis. This is the part. Now in this video I am going to perform response spectrum analysis. Before that, I already have the model. This is a model. This is ready, 44 story and 100 story as usual. We have 2 linear models. Let me show you. This is classical model analysis. We have 2 models, 44 story and 100 story. Again, linear times 3, the same thing, 44 and 100, and response spectrum analysis also the same thing, both 44 and 100, and pushover analysis and nonlinear times 3 analysis also. We have 2 buildings. So I have also video. So this part I am going to concentrate on response spectrum analysis, and we have 2 buildings, 44 and 100 story buildings, and we will see. But before that, so linear response history analysis, direct integration method or modal analysis, we will see also this one. Linear model response history analysis, this one also we shall see. Nonlinear dynamic procedure, nonlinear response history analysis will be included in my literature review, in my research as well. So before I continue, this is the whole research paper. So as per our research paper, this is the second part. This one, response spectrum analysis. So RSA 44 building and RSA 400 building, and this is the outputs and everything. So before that, I want to discuss why This work is a novel gap in the literature review. From extensive literature review above, one can in the last video I tried to show you that there is a gap for from extensive literature review above. One can observe that there were huge amount of work was done on the comparison of design of structures in different country codes, and performance-based design methodology was applied in different building types. But to our knowledge, none of them did intensive and comprehensive RC design on 44 and 100 story reinforced buildings, and include almost all type of design approach such as classical model analysis, RSA, response spectrum analysis. This is the objective of this video. Linear time tree analysis in linear model, and this static pushover analysis, and non-linear time tree analysis on non-linear model with plastic hinge modeling approach in one paper, and in the design location of Ethiopia also. So in addition to that, 11 ground data extracted from peer website are unique for this paper. This makes this paper novel and original, and open door for future research works. So as I try to mention, code-based design is not adequate enough to capture the non-linearity of our structure, and it will not give us the exact response of the global response of the structure. And so many researchers in last video I tried to show a lot of research works, literature review part. We discuss about this issue, and we try to see a lot of work was done on prescribed code based, and what is the shortcoming negative impact of code based, and why we transform to performance based design was discussed in the first part of video. So if you have time, you can check. So this work is novel. The location is Ethiopia, all is included, and the building type is also 44 and 100 story. So that's why we are going to do that. And a lot of researchers also, just to discuss, for example, in my literature review I try to show them, but a lot of researchers did a lot of things on prescribed code base. For example, this researcher, the traditional codes are developed for low and medium rise buildings whose responses are typically dominated by first transitional mode. Thus the codes use the global force reduction factor, R factor, which cannot predict accurately for the structure with significant inelastic response, especially in tall buildings. Furthermore, the traditional code attempts to satisfy implicitly the performance objectives, whereas the performance-based design explicitly mentions in such a way that the design satisfies the performance objectives for different levels of earthquake. So there is a lot of researchers also did on prescribed codes, the negative impact of prescribed codes, and other issues. This is also another work, but these all papers are included in my literature review work. This is also the comparison work. Indian standard code, Euro code, American code was compared with this sample building, and they came up with a conclusion. For example, the analysis as per ACI code shows more displacement, story shear, and story drift when compared with the IS standard and the Euro code. The displacement, shear, and drift is maximum for the first story for all cases. Comparing IS Indian code, Euro code, the displacement is increased by 50% for all stories as per IS code than Euro code. For Euro code and ACI code, the displacement is vary from 88% to 70%. This is the output of this result. So there was a lot of comparison works done in different research works, but as I said, this work will compare 44 and 100 story buildings, and for different kind of analysis, almost all kind of analysis, and we will have linear and non-linear buildings as well. So the work is novel already. So before I go to my research building. Before I go to here, let's discuss what is response history analysis and mathematical formulation. I will try to make it very fast, and let me try to discuss. So the response spectrum analysis, this is the response spectrum analysis procedure for seismic design of building structure, the concept of elastic response spectra. The prerequisite, this one is a concept in the mathematical model formulation of single degree of freedom structure. This is, we have to know this for the concept of elastic response spectra. Okay, so let's assume this is single degree of freedom system. Okay, if the system subject to PT in the single degree of freedom system, the dynamic equilibrium equation will go the governing quotient of n. This one is our mass, this is our displacement ut, this is our for example, we have damping, the inertial force, we have the inertial force because of m, we have the damping force here, and we have also elastic restoring force. If the structure subject to ground acceleration, in that case we can convert the effect of that ground acceleration into an effective earthquake force, ELF. That's why we call this ELF, because we can change this ground acceleration into a static. So P effective is equal to m times u dot g. So if we have u dot g times m, it will give us the force. So if this system subject to PT, the force PT here up, in the single degree of freedom system, the dynamic equilibrium equation will get the governing quotient of motion, the inertial force, the damping force, and the elastic restoring force, and the PT will be the applied force. So mass times u, this one is dot u dot t, plus this also the damping C, damping coefficient, times u dot t. K is here the elastic restoring force, times ut is equal to PT. So if we change this, the applied ground acceleration, into force, minus m times u dot g times t, this will be the governing equation of motion. So with this background, let's go to next here. Now we have that background. The governing equation of motion of single degree of freedom system subjected to ground motion u g dot. Here, if we have this one, we can directly find it from peer website or other. We will discuss later. So we can convert this. We can find the solution of our building dynamically or statically. So this is our governing equation of motion: m u dot t c u dot d plus k u t is equal to minus m u dot g t. From this, the C, our damping is 2m xi omega. From where we find this formula, we know omega square is equal to k over m RSA from classical modal analysis, and damping is equal to C over critical damping. Our critical damping is 2mw, so C is equal to 2m xi omega. So C is here, so we will replace C with 2m xi with omega here. Okay, after that we will divide m from all sides, so mass will be eliminated. So this will be our final equation. From this equation we can find our we can solve our equation of motion for displacement, velocity and acceleration. So output of the above equation, displacement, velocity and acceleration, are the dynamic response to the ground motion for the structure considered as a single degree of freedom system. Let's continue. So single degree of freedom system, I will come up with how to construct the displacement response spectrum and the pseudo pseudo velocity response spectrum and pseudo acceleration response spectrum. How we will construct, we will come up. But with this information, we have, if we have already the displacement, the maximum, this is single degree of freedom system, and we have ground acceleration motion, then we will for different time periods we will run our system, and we will pick the maximum. Okay, we will pick the maximum for each time period, and we will construct our displacement response spectrum. For example, 0.5 for 1 second, 1.5 to 3 seconds, and we will run this for different time periods, and we will construct, we will take the maximum of our response, and we will construct with time and our displacement in the y direction and our time period in x direction, and we can construct our displacement response spectrum, and we can convert that, we will see it in a minute, we can convert that also into pseudo velocity acceleration spectrum response spectrum, and pseudo acceleration response spectrum as well, and this will be for the given damping ratio. The damping ratio should be constant. So as you can see, if the damping ratio is very high, and the response spectrum will be down. If the damping ratio will be 0, then as the response spectrum curve will show higher, as you can see. So from once we get the displacement response spectrum, we can change it into velocity response spectrum with time, and once we get the velocity response spectrum, and we can change it into the acceleration response spectrum. We will see it in a minute, the whole idea as well. For example, single degree of freedom system, if we have ground acceleration, this is a ground acceleration, for example, we extract from perovskite, then for example, ground acceleration, deformation response of 3, single degree of freedom system with damping ratio of 2%, and the time period of 0.5, 1, 2. So once we have the single degree of freedom system, then the damping ratio should be constant, 2%, 2%, 2%. Then we will run our system for 0.5 second, 1 second, and 2 seconds. Then we will take the maximum. For example, here 2.67 inch. Then for 0.5 we have 2.67. Again we will run our system 1 second, 5.97. Again we run our single degree of freedom system, and we will get the maximum 7.47 inch. So we will approximately, we will connect this point, and then this will become our displacement response spectrum curve. Then we will use it, we will show you. So a response spectrum, a plot of peak values of response quantity as a function of the natural vibration period Tn of the system or related parameter is called the response spectrum of the quantity. The response spectrum provides a convenience means to summarize the peak response of all possible linear single degree of freedom systems. It also provides a practical approach to apply the knowledge of structural dynamics to the design of structures and develop of lateral force requirement in building codes. So this is how we construct the displacement response spectrum. Once we have our displacement response spectrum curve, then we can change it into pseudo velocity response spectrum and pseudo acceleration response spectrum. Just I am doing this because before we go to our analysis, this theoretical part, once we revise it very fast, very quickly, then we can continue to our final work. So pseudo velocity response spectrum, once we have our displacement, then we just multiply it by omega. Omega is 2 pi over t, then 2 pi over t times d, it will give us pseudo velocity. This is how we change it. Again, for pseudo acceleration response, w square omega square times d, it will give us pseudo acceleration. In this way we can directly convert the single degree of freedom system from displacement response spectrum into deformation response spectrum into pseudo velocity response spectrum and pseudo acceleration response spectrum. So as you can see here, a response spectrum with a damping ratio 0.02 for El Clasico ground motion. This is the El Clasico ground motion. So if we have this is displacement response spectrum, which we find from our single degree of freedom system. We run it for different time periods, and this is 2.67, 5.97, 7.47. So to change here from here to here, we simply multiply omega d. That means 2 pi over t. 2 pi over t. Okay, so 2 pi, we can, let me show you just for the sake of demonstration. So this is 0.5 second. We have 0.5 second. So 2 pi, let's approximate 0.14. 2 pi over t 0.5 times 2. This one, 2 pi over t is 12.56. Okay, 12.56 times d is 2.67 here. So times this times 2.67. So 33.53. This is 33.7 approximately. So this is how we change. For if you continue here, for example, times divided by 2.67. Pi is 1 here now divided by 2. This is omega times 5.97. This will be 37.5. In the same way, we can find this also. So we have d, then w square. We have 2 pi 3.17, 2 pi over t 0.5, 0.5. Okay, 12.67. 12.67 times 12, this is square, 12.68. okay, this times 2.67, this one, divided by, because this is in pound, 386.1, 1.111. yeah. So this is how we change from here to here. That this is for the sake of demonstration. So we have d, then we have the omega w, and that's why this one over g. That's why I let's continue now. So pseudo acceleration response, once we have the quantity A is related to the peak value of base shear VBO, or the peak value of the equivalent static force FSO. So once we have M, we multiply it with A, pseudo acceleration. So mass times acceleration will be force. So this force will be directly our equivalent static force. This is our equivalent static force. So here we have D, we have M, so we have K, restoring force, and when we apply FSO, the static force, equivalent static force, then the base shear will be considered. So we can analyze our building dynamically or statically. So the peak base shear can be written in the form of VBO, this is base shear coefficient, A over G will be our base shear coefficient, because mass is equal to weight over G. So we have the W, our the building weight, then A over G will be 0.5. So base shear coefficient will be like this. G will be approximately 9.8. So the combined DVA response spectrum, the three spectra, deformation, response spectra, pseudo velocity, and pseudo acceleration, are simply different ways of presenting the same information on structural response for a given ground motion. Knowing one of the spectra, the other two can be obtained algebraically, as we saw earlier. So this will be, for example, this is a combined DVA response spectra for El Clasico, El Centro, El Centro ground motion. So the damping ratio will be for the undamped case, for 0.02, 0.05, 0.1 and 0.2 damping ratio. As you can see, this is a graph. We have natural vibration period in this position, and we have pseudo velocity in this in the y direction, and this is pseudo acceleration, and we have pseudo, not pseudo, this is deformation response spectrum curve. So if you want to find any, for example, your structure is, for example, is 1 second natural vibration, then what we are going to do, we just go up and we will check the damping. For example, this 0 is the higher one is undamped curve, and the lower one is 0.2% damping curve. So we can continue like this: 0, 0.2, 0.5, 0.1 and 0.2. So if for example our damping ratio is 0.2 in our 0.02 in our case, that means this is the second curve. So we go up second curve, this is the second curve, then perpendicular we go here, then this value will be the pseudo velocity. Again we go up here, we will find here, then perpendicular to this it will give us the pseudo acceleration. Again from this point we go perpendicular to deformation. So this curve is the combined DVA response spectrum for El Centro ground motion, and for any place we can construct this kind of graph and we can use it. This is the same as that one, but a little bit brighter, that's why I brought it here. So as you can see, it will be clear here. We can see the graphs and the damping ratios, and this is deformation, this is pseudo acceleration, this is pseudo velocity, and this is natural period. Construction of response spectrum. So how to construct a response spectrum? We already saw it. We just run our single degree of freedom system with a constant damping ratio for different time periods, and we will pick the peak values. That is a point. So construction of response spectrum. The response spectrum for a given ground motion component U.GG, this is extracted from USGS, PROP site or wherever, can be developed by implementation of the following step. First, numerically define the ground acceleration UG.dot. Typically the ground motion ordinates are defined every 0.02 or whatever you want. Select the natural vibration period T and damping ratio, because we have to know that T and damping ratio should be constant for that period to pick the peak response. Compute the deformation response UT of this single degree of freedom system due to the ground motion UGT by any numerical methods. Then determine U0, the peak value of UT. So in this way we can construct our deformation response spectrum. Then we can change it into pseudo velocity and pseudo acceleration. Then the spectral ordinates, as we have discussed, D is equal to U0, this is a peak, then V is equal to 2 pi over TD, this is the omega D, and the acceleration will be 2 pi over T omega square over D. Repeat step 2 up to 5 for a range of T and Xi values covering all possible system of engineering interest. So present the result of step 2 up to 6 graphically to present the 3 spectral combined system like this. So sample response spectrum, spectral acceleration we have here, time period we have here, actual spectra of ground motions we have like this, design spectra also we have like this. So actual spectra of ground motions also we will have, but for the design spectra we might have this. This is just for the example, but we will see in the minute the exact meaning of this. So single degree of freedom system summary. As I showed you, this is single degree of freedom system we have. Then we have the applied ground motion. So we have the mass. So with constant damping ratio and time periods, we will run our single degree of freedom system, and then we will find the displacement, the peak displacement for each time period. Then we will construct our UT. After we generate our UT, then we can convert it into U dot D, and U dot T we can convert it into spectral acceleration as well. The same thing. So the whole idea is the same. Once we have the response spectrum curve for a given damping ratio, and if we have D for this the displacement response spectrum, then we can change it into velocity pseudo velocity response spectrum and pseudo acceleration response spectrum. Once we get that, A is WD, then once we get A, we multiply it with M, then it will become force ELF, then equivalent lateral force. Then we apply this equilateral lateral force as if our building is fixed support. Then we will proceed with ALF procedure to find the distribution of forces and shear forces, and all the application of center of mass and rigidity, everything as per the code. So RS provides a practical approach to apply the knowledge of structural dynamics to the design of the structure and development of lateral force requirements in the building codes. Response spectrum analysis procedure. So we will continue response spectrum procedure. So that's why response spectrum analysis is a pseudo. It's not dynamic and it's not static. So while constructing the response spectrum curves, we are in the dynamic part, because we are analyzing our project and this single degree of freedom system and picking the points and constructing the graphs, and that will be dynamic part. But once we have the response spectra of our site, we change the response spectrum, the dynamic system of our building into a static, and we will continue response spectrum analysis with ALF. As per our discussion, we have seen that RSA changed the dynamic equation of motion to static equation of motion. That's why RSA is pseudo dynamic analysis. So let's go to part 2. Now we know the mathematical formulation in very short time. Just what is response spectrum, now we know. Part 2, the mathematical formulation of elastic response spectrum analysis procedure for multiple degree of freedom system. So the vibration mode of structure and other orthogonality property of vibration mode is required for this. The elastic response spectrum analysis procedure. So the first, the classical model analysis concept was introduced by Arturo Donoso. This guy, he is the one who introduced the concept of classical modal analysis, and the concept of response spectrum analysis was introduced by this guy, Anthony Biot, and he was a student, and this von Karma is his supervisor. So just to mention. By the way, I'm using the lecture series from Professor Fouad Najim. I really appreciate him. He's a very helpful guy. So most of the things he explained was helpful to me for my PhD work. Okay, let's come here. Earthquake response of multiple degree of freedom system. So let's start here. A shear building subject to ground displacement UG. This is the ground displacement. We have UG. So this is ground displacement. Now we are going to see the mathematical formulation of multiple degree of freedom system, just for 4-story building here. This is also, I took this from Professor Fouad lecture. So as you can see here, ground displacement, we have ground displacement here, and we have structural displacement. U1, U2, U3, U4 is a structural displacement, and UG ground displacement. So this is the first point. So when we come to here, we can U total will be UG plus that means ground displacement plus structural displacement. This will be the total displacement, U total. So as you can see, UG plus this is for structural, this is for ground. So in the vector form we can put it like this: U ground 1 plus this one will be for structure. This is vector, and this one is only, we have 1 degree of freedom system only in the x direction. Now the other locations, the x, the y and the z is already locked for this purpose. So U total is equal to we have ground displacement plus we have structural displacement. So once we have U displacement, then we can have double dots, we can have the acceleration also. So once we get the displacement of the ground and the structure, and we can have also the acceleration directly by double dots. So mathematical formulation, we know from the governing quotient of motion, we developed from single degree of freedom system. We see that we have inertial part, we have elastic restoring part, this is damping part, and we have elastic responsive part. So mu dot dot total plus damping ratio times u dot plus k ut is equal to 0. This is equation of motion for multiple degree of subject to ground motion only. But as we have discussed here, u total is u total is ground displacement and structural displacement. So here ground displacement plus structural displacement, we are going to replace u total with this second equation. So, and we will take it to the right. So mu now this ground displacement will go in other side. M times ground displacement minus m times ug dot dot will go in the other side. So this will be our equation, and this equation is the coupled equation of motion. That means we have 4 equations, because we have 4, 1, 2, 3, 4. So this is the coupled equation of motion, and we cannot it's not easy to get the solution. So we have to decouple this question. This is the coupled equation, so we have to decouple it, and we have to transfer. So transferring the above equation into a principal modal coordinates, okay, so we will use this equation ut, this is ut is equal to phi, this is the mode shape, times q vector. This equation in general we call it, this equation is called modal expansion of displacement vector. So we have the displacement vector, and once we find the solution in the q vector, then we will multiply it with modal shape phi vector, then we will take the solution back to ut vector. So that's what we are going to do, where phi is equal to phi 1, phi 2, phi 3, phi 4. So phi I is equal to the i's mode vector, the i's mode vector. For example, we have here 4, so we have 4 modes: first mode, second mode, third mode, and fourth mode. And q also, q1, q2, q3, and q4. That's what we are going to do. So as you can see here, from 1 to 4, and phi high qi t. So this is how we are going to do. So this u vector, we have to use this equation to transform from here to here, but this will be very clear. We will do at the end of the day, we will do one practical solution. How what I am saying, we will discuss here, because this is also one of the work of Professor Fawad Najm, and I will show you how this will apply. So as we discuss here, ut here phi times q, okay. So we will see, this is the deformation, but we will see next, we will see it later what does it mean. So this is our equation now, mu dot 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 u plus cu dot t kut is equal to minus this one. So we are going to change u. As you can see, we are going to change the phi times q. Again here, c times phi times q dot t, k times phi times qt is equal to minus m1 u dot dot g. This is from directly from here. You just change u by phi times q. Phi is the modal shape and q is, we will discuss what it will be. It will be clear. Multiply with the transpose, phi transpose, and using modal orthogonality. This is very important to know, because using modal orthogonality we are going to solve this equation like this. So once we phi transpose times mass matrix times phi times q dot dot t, as you can see, this the result of phi transpose m times phi will be a diagonal matrix, and the off diagonal matrix will be values will be 0, and this the diagonal matrix will be modal masses. As you can see, modal mass 1, 2, 3, 4. This is the modal masses. Again, the same thing is phi transpose times damping coefficient times phi transpose times q dot t. This will give us 2 xi this modal mass times omega. This is also for 4. Again, this one phi transpose times k times phi qt is equal to this one. It will give us the modal stiffness. As you can see, modal mass times omega square. So this is equal to minus phi transpose m1 vector u double dot g. But we can, let's make L, this one phi transpose times m times 1, let's make it L. So this equation will become minus L u g double dot t. This will be modal stiffness. So where L again is, because we have 4, L1, L2, L3, L4. So L1 we change it by this. So as you can see, if you want to find L1, as you can see, for the for example, for the mode 1, fourth floor, third floor, second floor, and first floor, and we transpose the mode shape, and we will multiply with mass matrix, and we will multiply it with 1s, because we have 1 degree of freedom. So in summation form, this is in the matrix form. In the summation form, Li will be I from 1 up to 4, because we have 4 stories, mj times phi ij. So as you can see, phi I means the mode, first mode or second mode or third mode, fourth mode, or whatever. So this is the summation form, this is the matrix form. Now we reach here, let's continue. So the uncoupled equation of motion, this is very important. Now the uncoupled equation of motion, because we have 4 mores, so this one, for example, the mu1 times q dot dot t plus 2 times xi mu1 omega 1 times q dot t plus mu1 w1 square, this is modal stiffness, times this one times q is equal to minus L u g dot dot t. This is one equation. This is only contributing to the first mode, only the first mode. Then for the first mode we have 4 story, first story, second story, third story, and fourth story. So no contribution from the second mode, third mode, or fourth mode. So we have only the first mode here. So here, when we come here, the I's equation uncoupled. This is uncoupled equation of motion of the I's mode. As you can see, mu q dot dot t plus 2 xi this mass matrix w I omega q dot times t again mu omega square QIT is equal to minus L UG. This is for mode 1 only. There is no contribution from any mode. So this is I's mode. Then we have 4 stories: the first story, second story, fourth story. We will see now. So after this is very important point. After this we have mu, this modal mass, as we discuss now. We have phi I transpose mass matrix times phi I. This is for the I's mode. This is equal to, this is the transpose, as you can see. I shows the I's mode, and this one shows the story. Then times the mass matrix, first, second, fourth, third, and fourth, and times the phi transpose. This is the phi, as you can see, for the first mode only. Then the first, second, third, fourth stories. This is in the matrix form, and this one is in the summation form. The summation form from 1 up to 4, m times j phi I square j. This is in the summation form. So let's continue now. Modal participation factor. Modal participation factor, it means gamma I is equal to Li over mu I. Okay, Li over mu I. So phi transpose times m times 1. This is as per our assumption in the first slide. And mu phi transpose times m times phi I. Then this will be the mass participation factor. But in ETABS I will show you what does this mean. In ETABS I will show you what does it mean. For example, just sake of demonstration, this means in our demonstration display table structural output modal information. No, we don't need this, and we don't need this. Only I need modal, this one, this modal participation. This is modal participation. As you can see, our the first mode around 71.87 mass of the building is participating in the x direction. So this is the first x dominant translational in the one direction only, because ux and uz are 0 only in the x direction. This is the second is in the y direction, and the third is in the z direction. So we will see this one when I come. Just for your information, I came now. So this is how participates the I's mode response to the ground vibration. So the I's mode equation becomes, so if we this one we have mu I. If we divide with mu I here, all mu I, then we will find q dot t plus 2 xi omega QIT plus omega square QT is equal to minus, as you can see here, we have L over mu I will be this modal participation factor. So we have minus R UG dot T. Divide the whole uncoupled equation with mu, then we will find this is the final equation we have. So we have the modal participation factor. Now this is the main issue. So uncoupled equation of motion. Now we have the uncoupled equation of motion for each one. So uncoupled equation of motion, we have elastic modal response history analysis, RSA analysis procedure, and we have a response spectrum analysis procedure. So these two are very different. This one solves the uncoupled equation of motion for each significant mode represented by the single degree of freedom system, and sums the dynamic response to get the dynamic response of multiple degree of freedom system. So this one will be we will get it from here, because we get already the uncoupled equation of motion for each mode. Then we will find the response of each floor, and to find the final response of the structure, we have to sum the whole uncoupled equation. If we are doing this is called the elastic modal response history analysis, RSA procedure. This is dynamic analysis procedure which gives us total history of the response, because once we have the uncoupled equation of motions, then we can do for each equation of motion, and we will sum up to find the final response of the structure. But the response spectrum analysis is, as we have discussed, what we are going to do from single degree of freedom system with the applied UG dot dot, then for the constant damping ratio, and for time period we will run it and we will pick it the maximum, and we will construct the response spectrum, this displacement response spectrum, and from displacement response spectrum we will change it into spectral acceleration and pseudo acceleration. And from that, for our building, we will find, for example, for our building, if our time is, for example, this is Ti, then we go here and we will find SD. Directly we will find SD, and we will change it into pseudo acceleration and pseudo velocity. And after we find the response of the structures, then we will SRSS them, or CQC method. We will use these two methods, or we have also the third one, but mostly for this purpose we are going to use for SRSS method, square root of sum of squares of the responses of our structure. So if we are doing directly picking the peak response of each significant mode represented by the single degree of freedom system, and approximately combining those peak responses to get the peak response of multiple degree of freedom system. So if we are doing this, we are doing the response spectrum analysis procedure. So this is very easy compared to this one. This one is dynamic analysis procedure which gives us peak responses only, but this one is dynamic analysis procedure which gives us total history of responses. So this is the difference. But for our cases, starting from this point, now we identify even response spectrum. We have two types of response spectra. So starting from this, now we are going to use elastic response spectrum analysis procedure, this one, because ETAPS also use this one, and we are going to do that. So the Eigen mode equation become, as we discuss, the maximum deformation in the Eigen mode. So this is UG dot dot. This is the UG dot dot. We construct displacement spectrum, and this is our time period. Then we will pick Q max. Q max, this is, as you see, the maximum deformation in the Eigen mode. QI max is maximum deformation. The maximum deformation is equal to mass participation factor in the Eigen mode times spectral displacement in the Eigen mode. So if you multiply this, we will find QI max. Okay, QI max. So after we find QI max, U max is equal to this one, mass participation factor times with the mode shape. When we multiply it with the mode shape, then with the spectral displacement, we will find U max. Once you find U max, SDI is determined from elastic response spectrum at a given Ti, and Xi is constant. So once we find this, we multiply this, then we will find U max. That is how we are going to do. After we find U max, if you want inter-story drift ratio, as you can see here, we can find the same thing, but upper story minus lower story, the mode shape, the mode will be minus, then we will find inter-story drift ratio. In this way we can find like this. This is elastic response spectrum analysis procedure. Again here, the elastic response spectrum analysis procedure, the equivalent static force corresponding to the I's mode, the force which will deform structure in the UI max, shape and magnitude. Once we find U, Ku will give us F. So this is how we are going to find our force. So once we have the U max in the I's mode, then in that level of our building we will multiply with K matrix, then we will find it the equivalent static force. From eigenvalue equation, this is the eigenvalue equation, K phi I. K phi I is equal to omega square m times phi I. So let's change K phi I with omega square m times phi I here. So we have mass participation factor omega square mass matrix phi I times SDI. So this is how we are going to do. We have mass participation, this is omega square, this is SDI, mass matrix and phi matrix. For 4 floor we have 4 because our example is 4. Then this equation we can find FCI. This is the same equation we have. This is the same equation. This is so the equivalent static force for each mode. This one step we have seen this in the previous slide. Once we have the spectral displacement, we multiply omega square, we change it into pseudo acceleration, SA. Yeah? So the same thing we are doing here. Once we have SD, we multiply it W square, we multiply it here, SD, okay, SD, so W square times SDI, W square times SDI. This is SA. Yeah, SA will be W square SDI. That's how we find here. So R times M times phi times SA, because SA over W square will be here, SA over W square will be here, W square will be cancelled by W square. So the force, the equivalent static force for each mode will be this one. So SA determined from elastic response spectrum at Ti and Phi for each mode. So it will be constant. The only thing which will be changed will be phi, because if the shape of our building is, the first mode is like this, if our building is like this, then first mode, second mode, third mode, fourth mode, so the phi value will be different. So everything is constant, the only thing will be phi will be different, because that time period, the mode shape of the first mode shape, second mode shape, third mode shape, it will go. So for each floor it will go like this. So once we find this is FSY, this is for mode 1, then we will find for mode 2, then we will find for mode 3. So all the reactions, the response of the structure, whether shear force, moment, inter-story drift ratio, or anything, we will SRSS them to find the final response of the structure. So as you can see, each mode has its own response. I will show you this with a worked example. Okay, I will show you this with worked example. 44-story building. I will show you this the result of this is mode 1, mode 2, mode 3. What I am telling you now, this is mode 1, mode 2, mode 3, and how we are going to do this, all the forces, U maxes and SA, how to change it, how to bring it, how to make spectral acceleration and damping ratio, everything we will discuss just in a minute. After I finish this one, we will continue, then you will understand very well. So this is modal combination rule. As I told you, SRSS, this is sum of square root of sum of squares of the peak responses from each mode suitable for well separated natural frequency. This is SRSS. complete quadratic combination is applicable to large range of structure response and giving a better result than SRSS. These different researchers, they show that, but ETABS has both SRSS and CQC for our result. Again, this one absolute sum at the absolute maximum value from each mode, not so popular and not used in practice. This is modal combination rules. Now, the elastic response spectra. Summary. As we have seen now, determine M and K matrix and xi for a constant xi. Then Tn eigenvalue analysis. From eigenvalue analysis, we will find the mode shape and the time period of each mode. First mode, second mode, third mode, fourth mode. Compute peak modal response of each significant mode for each ith mode. So for I, Ti and xi, peak spectral acceleration and spectral displacement from a spectra. Then compute a story displacement and inter-story drift ratio, also the same. This is the formula we are going to use. Mass participation factor phi times SDI, it will give us Umax in that floor. Again, inter-story drift maximum upper floor minus the lower floor times mass participation factor SDI, it will give us this idea. Compute equivalent static force. This is the force as we discussed. Mass participation factor, mass matrix, phi SAI in that floor. All in that floor, in that mode and in that floor. Compute all responses by static analysis of structure using FSI. Then we find all the forces in each floor. Then estimate peak responses by combining peaks of individual modes. For each mode, responses usually lower modes contribute significantly, because if you have 50 mode or 100 mode, we don't use 100 or 50 modes. Maybe as per code, 80 up to 90% of modal mass participation is required. So in most cases, the first 3 or 7 modes will contribute to 80 up to 90% of the modal participation. Then there is no need to do all the modes in our buildings. Note, this is as I told you, I took this slide, very nice slide from Professor Ford Najim. RSA reduces the dynamic problem into static problem. So in response spectrum analysis, once we developed our response spectrum for our site, that is the dynamic part will stop there. Then it will change it to the static problem. In fact, a series of static analysis using FSI, equivalent static forces, for few modes. RSA still retains the feature of dynamic analysis to, as I told you, fundamental period, xi, omega, phi. To find all these things, we have to run our system to find the mode shapes, and so the dynamic part of the problem is already done while developing spectra. Once we are doing the spectra, SDI versus T and SAI versus T, that's why we call it pseudo dynamic analysis. So the difference between response spectrum analysis and response history analysis, as I showed you, the difference between, we have two type of response spectrum. We will come back here. This one, elastic modal response history analysis and response spectrum analysis, they are different procedures and they have some differences and similarities. This one is once we get the uncoupled equation of motion, and we have to calculate, we have to find the solution for each mode and for each floor, and we have to add up all solutions to find the result. So that is the issue. So we came here 36 RHSA and RHA. The difference, Umax is the same for both of them. The same peak displacement from RHA, because the spectra is already based on a response history analysis. So Umax, which is found in the RHSA and in RSA, both are the same. But Umax from modal combination rule is not the same as peak displacement extracted from RHA result, because RHA we have to calculate each uncoupled equation of motion and we have to find the result. But when we pick the UHA from modal combination, it is not equal. The direction of FSI is controlled by algebraic sign of the phi, because the force will have the same direction as this is the first mode, this is second mode, this is third mode. Again, this is a pitfall. Avoid the pitfall in RSA response history, response spectrum analysis, calculating one response from combined peak of other response is wrong, because once we get from first mode the responses, and second from the second mode, and the third from third mode, then we cannot add, we have to SRSS that, because it's not equal. Or we cannot simply from first mode to second mode, from third mode to fourth mode, we cannot minus or plus. Even IDR also, inter-story drift also, is not right. We have to do each for each mode. I will show you in a minute, and we have to do that. The combined force, everything should be like that. So to finalize this issue, as we discussed, we have ground motion, then we have our building, then we will change it into PT, then m times UG dot dot. Then this is structural model, then eigenvalue for each time period for first mode, second mode, third mode. Then we come here, spectral acceleration for from the first we will find, then second, this is third mode. Then we will find the force F1, F2, F3. Then we will find the responses. Then we will combine it with SRSS or CQC. This is the final procedure. So response spectrum, the mathematical formulation, single degree of freedom system, multiple degree of freedom system. What is the difference between a response spectrum and response history analysis? For response spectrum analysis, we have to use the maximum responses, but the response history analysis, we have to decouple the equation of motion. The coupled equation of motion should be decoupled into uncoupled equation of motion, and we have to solve the response of the structure for each mode and for each floor, and we will SRSS them at the end of the day to find the response of the structure. Equivalent lateral force versus response spectrum analysis. Static modes specified in building codes are based on single mode response and appropriate for simple and regular structure. This ELF only for simple structure, and mostly they don't incorporate the higher mode effects. That's why in our research question, in the first research question, this is also asked, why, if it is okay, I mean, or if you have to, we will come later that point, but let's continue now. Dynamic analysis should be used for complex buildings to determine significant response character. That's why. Effect of structural dynamic character on vertical distribution or lateral forces. Increase in dynamic load due to torsional motions. Influence of higher modes resulting in an increase in story shear and deformation will be considered in dynamic, but it's not in ELF. The code-based response spectrum. So with this background now, we know what is response spectrum, the mathematical formulation, and all these things. Now we will see the code-based response spectrum. This is UBC 1997. As per UBC 1997, we will see the concept of inelastic response spectrum and dynamic spectra, design spectra. Evolution of seismic design factors, R factor, omega factor, CD factor in the building. Evolution of the concept of ductility in the building code will be discussed in this part. Very fast, I'm going to finish it now. This is the two people which contribute a lot. The code-based response spectrum analysis RSA procedure. This is Ray W. Glove and Edward L. Wilson. These are the two people who contribute a lot on the code-based response spectrum analysis procedure to incorporate it in the code. So the standard response spectrum procedure ASC 710 and IBS 2012 and EC 8 European Code 8, what they are going to do is, this is linear elastic model. We have linear elastic model, then we just perform eigenvalue analysis. This is k omega square m phi analysis and determine the mode responses. So we have Ti, phi and mass participation factors, everything we will find this. After we find this, determine spectral acceleration for each significant mode. For each significant mode, mode 1, mode 2, mode 3, and we will come here, we know the time period for mode 1, and we come here T1, then we will find SA1. And again we run this for T2 and we will find the response. And we will find T3 and we will find SA. So this is spectral acceleration time graph. For initial viscous damping, so fixed damping ratio. So as you can see, we will find SA from here. Then this is determine elastic base shear. To determine the elastic base shear, once we find SA here with this formula, modal participation times mi times phi n SA from this, then we will find the base shear for the reaction for each mode, mode 1, mode 2, mode 3. So VB1, VB2, VB3 we will find from here. Then we will SRSS them to find the total response. So as you can see here, VB1 square, this is V elastic. V elastic will be VB1 square plus VB square, VB2 square, then root, then we will find V elastic. This is the elastic base shear. The elastic means we don't apply anything here until this. Then this is SRSS. Now starting from this point, when we come here, the code base will start. So as per the code, reduce elastic base shear to account for inelasticity, for the ductility. So as per the code, this is a V elastic, for example, our V elastic base shear, V elastic is here, but as per the code recommended a response modification factor ESC7 or behavioral factor ESC8. What they are going to do, we will use R. So by V inelastic is equal to V elastic, the elastic response we find, divided by R over I factor. Then it will give us the reduced level from here to here. So this is for the considering the ductility and the ductility factor of our structure. So we will decrease it. Instead of going up like this, when the earthquake comes, our structure will behave in this way. Okay, in this way. So roof displacement, even the roof displacement elastic will be changed into roof displacement inelastic. So V design, the design base shear will be the SRS value we find from elastic divided by R over I. This is for ductility factor according to the codes. Again, moment also the same, divided by R. Again, this one CD factor. So we have CD factor for any deformation, displacement issues. We have CD factor. So as you can see, CD X over R over I. So CD over I. CD is around 0.7 R as per UBC calculation. So omega, we have structural over strength factor. This will be applied if we want some of our structures will remain elastic at the occurrence of earthquake. So if you want some part of girder beams or other things to be elastic in that period, so we will apply omega. For members not desired to yield during a design earthquake, we will apply omega. omega times V elastic over R will be applied. So we will see this also in the next. Maximum displacement during a design earthquake, this one XR max here. Mostly it is the same, because here our structure will ductile start from here, this one XR. So what we are going to do, we have to amplify it, CD factor. So we will apply CD times XR over importance factor, because it will go until most of the time the elastic displacement and the inelastic displacement are almost the same, not that much vary. They are almost the same. So CD is equal to 0.7 R as per UA. So displacement amplification factor, CD is equal to displacement amplification factor. This is how we are going to use CD over R over I. I is importance factor for all. So this is a general procedure for code-based response spectra. This is I already discussed. The input output summary. Input needed in the response spectrum analysis: mass and stiffness distribution, a simplified response spectrum curve, the response input direction, the response scaling factor, the number of modes to be included, output from response spectrum analysis, on-site displacement, because the displacement will be on-site, there is no plus or minus, we will see it, stress resultant and everything, because this one unsigned means SRSS means sum of square root of sums, any negative or positive. When we square root, it is positive, so it will be positive all of the time. So this is the response spectrum procedure in UBC 97. A response spectrum analysis. Directly we can see, we can read from them, but it will guide us. This is prescribed code based, so we have to follow. As you can see, this is UBC 97, response spectrum analysis, response spectrum representation, interpretation of results. The ground motion representation shall be according to section 163.1.2. The corresponding response parameter, including force, moment and displacement, shall be denoted as elastic response parameter. Elastic response parameter may be reduced according to section this. So as I told you, ductility, R factor over strength factor, CD factor, all these factors will be included. Number of modes, the requirement of section, this that all significant mode be included may be satisfied by demonstrating that for the modes considered, at least 90% of the participation factor, mass of the structure, is included in the calculation of the response of each principal horizontal direction. So a minimum of 90% is required in the UBC 97. Combining method, the peak member force, displacement, story forces, story shears and base reaction for each mode shall be combined by recognized method, SRSS, CQC or absolute sum. When 3-dimension modes are used for analyze model interaction, effect shall be considered when combining modal maxima. In this way we can see, for example, reduction of elastic response parameter for design. Elastic response parameter may be reduced for purpose of design in accordance with the following item, with the limitation that is no case shall the elastic response parameter be reduced such that the corresponding design base shear is less than the elastic response base shear divided by the value of R. So this is for code spectrum for all regular structures where the ground motion representation complies with section this one. This is for the code spectrum. Elastic response parameter may be reduced such that the corresponding design base shear is not less than 90% of the base shear determined in accordance with section 160. So this is one of the point in our research question. My question was, if we perform any dynamic analysis and the base shear we are going to find from dynamic analysis should not be less than the ELF procedure base shear we found here. If it is less than, then we have to scale it up at least to become 90% of the ELF, equivalent static procedure. Very important point for our research as well, and that is the question. So the main point is ELF will not consider the higher mode effects, but even if it doesn't consider the higher mode effects, the base shear which is found from ELF static procedure should not be less than the dynamic any response spectrum analysis or time history analysis, whatever we do, the base shear or the any response we find from this should not be less than the equivalent static procedure. That is the point. So as per response spectrum UBC 97, this is a response spectra. We need CA and CV. This is design response spectra. This is the formula. Once we find we have CV, CU, and this T, TO, and T 2.5 CU. It's very easy to construct as per the code. So just to finalize, this one is earthquake has different intensity. We have service level, design level, maximum level. This is 10% in 15 years, 50% in 50 years, 43 year return period, and 2% of probability of being accidents in 15 years. So always we are for code based and for our design always we use dB level, but for performance based we have to use MCE level. Once we have MCE level, 2/3 of MCE level will be dB level. This is also response spectrum as per IBC code. IBC also, they have also their own code. They recommend modal response spectrum analysis, linear time history analysis, non-linear time history analysis, modeling. This is the modeling part. The mathematical model of the building shall be constructed that represent the spatial distribution of mass and the stiffness throughout the structure. For regular structure with independent orthogonal seismic force resistance system, independent two-dimensional model may be constructed to represent each system for irregular structure without independent orthogonal systems. You can read it. So this is how IBC going. For IBC and UBC are different. IBC they use SS and S1 hazard map. Of this is a hazard map of US. They use SS and S1, not zoning. In the UBC we use Z factor, the importance factor, for calculation of base shear acceleration. But in the IBC we are using SS and S1 in the 1 second and short period. As you can see, determination of FA and FV factor, site classification, definition. So from here we will find, for example, site class, soil profile name, hard rock or whatever, soil shear velocity, standard penetration, soil undrained shear, and because as per this we will take our from here we will pick our site class. Then once we know our site class, and this is site coefficient FA modification for short period of responses. Once we know the SS from SS and S1 curve, once we know SS from here, if your position is here, then you will read SS. Then you know the site class, then you will know FA. The same thing is true if you know S1, then you know your site class, then you will read from here, you find FV. Then once you know SS and SS, S1 and SS and S1, then you know FV, FA and FB, then you will find SMS and SM1. This is design spectral value for IBC 2000. Then this is for design, this is MC level, maximum considered earthquake level. This one is for dB level. As I told you, 2/3 of MC level will be design level. We will design for this one, and all the explanation what is it we can read just to minimize time. let me pass, but everything is written. What is SDS, what is SD1, what is TO, TS. Once we find this and calculate, automatically come here, we know TO and we know TS, because here T fundamental period of the structure, TO is 0.2 times SD1 times SDS, so 0.2 times SD1 over SDS will be TO, SD1 over SDS will be TS. So you have TO, TS, and 1 second SD1. We will find here we have SDS. This is constant acceleration point, this is constant velocity point. Then for longer period we have constant displacement section also, but for most of the buildings we have around 4 seconds, 5 seconds. So we have always constant acceleration and constant velocity period, not constant displacement. So in this way each code will have its own site. This is IBC 2000, you can read it. Modal property, the required period, modes analysis shall be conducted to determine the normal modes of vibration for the building, including the period of each mode, the modal shape vector phi, the mass participation factor in the modal masses. The analysis should include a sufficient number of modes to obtain a combined modal mass participation of at least 90% of actual building mass in each two orthogonal directions. This is also the same. The only difference between UBC 97 and IBC 2000 which I notice is that when we see the Becher which we find from ELF and from response spectrum, if it is lower, how to scale it, that has in the UBC 97 only we will divide the Becher and the scaling will be directly applied, but in the IBC 2000 the history is different. In the IBC 2000 there is a CD factor and other factors also, but in the UBC 97 that's not the case. So this is the modal seismic response coefficients. Yeah, this is what I told you. In here it will be included. This is design coefficient and factor for base seismic force resisting systems. So the R factor, omega factor, CD factor, everything will be written from the table. So as per this discussion, let me show you, before I go to my our research, let me show you what they did. This is a response spectrum analysis for 44-story building. This is the response spectrum analysis for 44 building. This is also from Professor Fouad Najim presentation, and as I showed you the modal cases, modal Eigen it's used, and if you see 20 modes are considered, and Eigen value not reached, we are using Eigen, and 20 modes are considered. Let's cancel it. And the response spectrum define function response spectrum. RS is defined already. Modify show. As you can see, this is the response spectrum for the damping ratio, 5% damping ratio. This is the response spectrum as per ACE7 is used. Now what I want to explain is a response spectrum analysis. This is the software output, but I will show you the Excel output also. For example, this is the Excel output. So how we are going to construct the Excel and the ETAPS output. This is a time period. We have T1, T2, T3. So this is a time period. So I am going to show you from the mathematical formulation of single degree of freedom, multiple degree of freedom. We already see all these formulas. So how we perform response spectrum analysis, I will show you now. So first we will pick these points, the time period. So we go here, display, show table. So here, from here, display, show table. We will see structural output. I need modal information, mode participation factor and modal period. We don't need, okay, this one later we will need it, but not now. Okay, as you can see, the first mode we have 4.782 second for the first mode, and the second mode we have 4.21 second, and third mode we have 3.848 second. The mass participation factor is the first in our building. It is translational in the x direction, and 72.23% of our building is participating in the x direction, and in the mode 2 we have 66.26 mass of the building is participating in the y direction, and mode 3, as you can see, it is torsional, rotational, and we have around 73.36% of our building is participating in the y direction. But as per software numbering, mode 1 means it is translational, pure translational in the x direction. Our building is in the pure translational in the x direction, and 72.23% of the mass of our building is participating in the building. Mode 2 means it is the first mode, again the first mode in the y direction, and 66.26% of our mass is participating in the building. Mode 3 means for 73.36% of our mass is participating in the z direction. So mode 1, 2, 3 means it is the first mode in the x, y, z direction, and mode 4 means the second mode in the z direction, the second mode in the x direction, and mode 5 means the second mode in the y direction. So this is what we do. And 6 means the second mode in the y direction, and 7 means the first mode in the x direction, and 8 means the third mode in the y direction, and 9 means the third mode in the z direction. This is the numbering. So when we come to Excel, as you can see here, the first mode is T1, it's around 4.544, and T2 okay, the second mode 1.411, and the third mode we have 0.719 approximately. So we need, because we are checking only in the x direction, that's why I am using this one, first, fourth, and seventh. This is first and fourth and seventh. This is the time periods. So let's approximate. This is the time period. This is the time period. So we have the time period here. A spectral acceleration, we directly pick from this curve. So we have a response spectrum, and we have time period here. So for different damping ratio, for 5, 6.5, 7.5, 8.5, 9.5, 10.5, 12, 15, we have the spectral response spectrum acceleration. This is the time period, and this is the spectral acceleration values. So we can directly pick from here, or as I showed you from here, we go to define a response spectrum, and from here we can see this is our site response spectrum for this particular site. So as per this one, you can see here spectral acceleration values for each time period for each mode. The first as per software numbering, first mode, fourth mode, and seventh mode. This is a time period, and we have a spectral acceleration. We directly pick from our response spectrum for 5% damping ratio. And spectral displacement means omega square times, as per this is the formula, spectral acceleration is equal to omega square times spectral displacement. So once we have a spectral acceleration, we can multiply with omega square and we can find the spectral displacement. So this is the formula for spectral displacement. After this, maximum number of 90% of the mass participation factor in our building is the three modes. The three modes already reach more than 90%. So we will consider mode 1, mode 2, mode 3. This is a time period we already brought from 4.544, 1.365, 0.76. This is mode 1, mode 2, mode 3 time periods. And mode participation factor, I will show you here how we calculate the mode participation factor. We have another spreadsheet. The damping ratio is 5%. The spectral acceleration, we directly brought it from our spectrum. And the spectral displacement, we have spectral acceleration omega square times sd square. This is pseudo acceleration formula. Then we will find it from here. So damping ratio is 5%. Now level, this is our building. We directly extract the data from our building. We have 44-story building. So this is our 44-story, and this is the elevation of our building. Directly from table, we can find the data, display table, and we will bring the data from here. And the mass also, diaphragm mass of our building, directly we will find it from here. Just to show you, show table, structural output, element joints, okay, mode participation factors, outputs, this one, center of mass and rigidity. Let's close this one. Okay, center of mass and rigidity. Okay, okay, it's extracting. It will take some time. Okay, so as you can see, this is the mass. This is the mass. Directly we will take it from here to our Excel. As you can see, this is our mass, but we will story mass in the X direction. We just copy and paste. This is elevation. So the elevation, we have the elevation. Now mode 1, mode 2, mode 3. This is the mode shapes. This is the mode shapes. Directly from where we will find this one, we will go here, display story response plots. From story response plots, as you can see, from modal cases, this is mode 1. Then directly we will take it from formatted. This is the mode shapes. As you can see, x1, okay, this is elevation, this is location, this is x in millimeter, this is y in millimeter. This is the mode shapes. Or unformatted, for example, you can see here This is a formatted one and that is unformatted one. So we will take this mode shape, we will take to this mode shape here, but our 44 story is down, so this is the mode shape one for us. Then mode 2, again for mode 2 we will come here, and we will change it to mode 2. This is the mode 2 shape, this is the mode 2 shape. Again, this is formatted or unformatted, this is the mode 2 shape. So we just copy XLS, we will take it there. Again, modes, but for us it is mode 4. Mode 4, the second one is mode 4, and the third one is mode 7 as per computer. So in this way we will take mode 1 shape, mode 2 shape, mode 3 shape, mode 1, mode 2, mode 3. Then we will normalize the modes. This is mode 1 shape, so we will normalize it by dividing the maximum. As you can see, for the mode 1 I divided it with the maximum 1, so this is divided by the maximum 1. Again, mode 2, this is normalized one, mode 3 it is normalized one. So everything is normalized in the mode. Here let's go to mode participation factor now. This is modal participation factor. The modal participation factor is, this is a formula, as if you remember in the multiple degree of freedom system, the formulation of the equation, this is mode participation factor in the matrix form, in the summation form. So this is, we have phi, the mode we extract from ETABS now. So this is a mode shape, phi transpose m times 1 over phi transpose m times phi. This will be the mass participation factor. So in the summation form we have here summation of mj each floor, phi in each floor, summation of that over summation of mj phi j square. This will be the modal participation factor. So as you can see, m times phi square for mode 1, for mode 2, for mode 3. So all will be here. Then summation, sum, we will sum it and we will divide it by the total summation of mi square. So this divided by this one, this divided by this one. So mode participation factor for the first mode is 1.4081, for the second mode minus 0.61136, for the third mode 0.3579 is our result. So we go here, this is the modal participation factor for the 3 modes. Damping ratio, spectral acceleration, we took it from here. Then spectral displacement we have here. So mode 1, mode 2, mode 3 data from here. Then we come here, we normalize it, the mode shapes. Then story displacement, we have the formula w u1 is equal to as you see the formula, I can show you, mode participation in each floor times mode shape times SDI. So SDI for mode 1 we have here, for mode 1, and for mass participation factor R1, this we calculate it now. Mass participation factor we have here. So the only thing it will change is the mode shape along the building. So as per the mode shape, this is the displacement. So if I, for example, displacement, as you can see, the time period, we have this so we have modal participation factor, we have spectral displacement, we have time period, and so as per this it will calculate SD spectral displacement. Then story displacement will be discussed like this, or in both ways it is the same. It is the same, because we have spectral acceleration also 2 pi over t also w, so 2 pi over t square, SA over 2 pi over t square also a story displacement. So this is the formula we have, phi I times this. So absolute story displacement, any negative we find here, we will be absolute value, we will change it into absolute value. Then inter-story drift, this is upper minus lower from here to here, here to here. Elevation, we have elevation, then we have here. So as you can see here, U14 minus U13, upper minus lower over story height, this minus this. So in this way we can find absolute shear. Then absolute story displacement, sorry, absolute story displacement, then inter-story drift, then story forces. Again story forces, we have modal mass. Here we have modal mass, where is it? Sorry, the modal mass, yeah, mode participation factor here, times mass times phi times SAI, spectral acceleration in the eye. This one will give us the force. This is the force. Then story shear, just multiplying the upper, from up to the level, we will find the story shear. So this one will be all included, because from 0 to this is 0 level, so the whole is the story shear. Then we will decrease 0.3, then here, like that. So story moment, for the story moment, again this guy, he did this, then the story forces times the height, then elevation, then this formula will give us the story moment here. Then the absolute story moment, this is also we make it positive. So the same thing will be true for mode 2 and mode 3 as well. After that we will come to the same thing is true. Then if we use any specific code, we have response modification factor, R factor, we have overstrings factor, we have importance factor, we have displacement amplification factor, CD factors. Each code, UBC 97, IBC 2000 or everything, they will have their own number. So let's assume for this demonstration, this is response modification factor. So now as per previous discussion, this is combination of SRSS elastic response formula from all modes. This is story displacement, inter-story drift, story shear, story moment. Then we will SRSS them for the 3 moments. We cannot take from one, because this is response spectrum analysis. So we will, in this way, SRSS combining by SRSS, we will find the response of the building as per response spectrum analysis. Then as per the code, for the design forces, for shear, story shear and the story moment, we can multiply by I over R. This is for inelastic consideration. So I over R, we can multiply this by I over R. This is I over R. Then we will find the design forces and design moments. And displacement also CD over CD times I over R. So this is also as per the code. We will multiply all the story displacements and inter-story drifts. Anything which is related to displacement will be multiplied by this one. Overstrings factor, if we have any structure in our building that we don't want have to go to it will be remain in elastic in the during earthquake, then we can multiply it by overstrings factor. That means omega times I over r. So omega, we have the overstrings factor, this times I over r. So this will be the result. This will be the result. Then as per the result, we can see here, this is our response spectrum curve. This is the same response spectrum curve as here. This is the same response spectrum as here. Define response spectrum here, response spectrum, apply. This is the same response spectrum we are using there. Sorry. So this is the first mode, second mode, and third mode. So if you see here, go here, modal analysis, first mode, apply. This is the first mode, and the second mode and the third mode also the same way, but let's instead of 3D, let's plan. Sorry, let's make it elevation to make it clear. Apply. Okay, apply, close. Now apply. I want to see. Yes, this is the first mode. Second mode, sorry. So in this way we can see the second mode, so you can see. So this is the first mode, this is the second mode, and this is the third mode. This is the second mode, and this is the third mode. Again, individual mode responses, as you can see, mode 1, mode 2, mode 3. The mode 1 is significant. Mode 2 and mode 3 are very low, as you can see. And IDR, inter-story drift ratio, also the first mode is here, and this, as you can see, again the first mode for story shear, and the second mode and the third mode. Again, overturning moment, this is an individual mode response, the first mode, second mode, and third mode. If you continue down, this is the combined response. This is the combined response, means the same response can be seen in the ETAPS. So we can check it like this. We can go to ETAPS, story responses. The first one, for example, story displacement, RSA, as you can see, 1264. So if I come here, sorry, story displacement, yeah, yes. Wait, let me change this one. Let me change this one. This is story displacement combined, and this one is the maximum is around here, and this one also here. So if you go here, name RSX, yes, this is RSX, RSX, sorry, a story range, all, okay, a story responses, maximum story displacement, next, and this one. For example, a story drift, a story drift also, as is story displacement. Sorry, it takes time. The same combined response is noticed here also, but it will take time. It will take time. When it comes, I will come and I will show you displacement, inter-story drift, story shear, and overturning moment was extracted in the Excel. Not responding. Okay, so as you can see, this is the mode 1, mode 2, mode 3. This is inter-story drift ratio, this is overturning moment, and combined response elastic. This is individual, this is combined response elastic. The same thing, the result is supposed to be the same. Because of this I cannot show you now, but I checked it already, because we consider only first, second and third mode. There is not that much, but not that much, but there is a few difference. But my laptop is I don't know what. Okay, this story displacement. For example, the story displacement is 1.1%. This is combined response. As you can see, it's around there. It's around there. Okay, this is percent, 0.13% maximum, and the story share. Story share maximum story share it will take time, because it is 44 story building, I think. Yeah, this is story share. So as you can see, it's around 76. Let's go here, story share. Yeah, so approximately it is the same, but considering because we are using 3 modes, but ETABS will consider the higher modes also. That is only difference. That is only difference. Okay, in this way we can extract and see overturning moment, but it will take time, and other results. So here individual versus combined. As you can see, the combined is here, the individual is here. So the individual and the combined has a little bit difference because of the higher mode effect, because we consider 20 modes, but here we consider only 3 modes. So the higher mode effect will not be included here. That's why this difference comes. Again, combined elastic response with design demand. The design demand is already divided by R factor and CD factors. So this is the difference, the elastic and the design. This is the displacement, this is inter-story drift ratio, this is story shear. Even the story shear is a huge difference. Overturning moment also has huge difference. Elastic demand versus design force demand with and without overstrings also we can see here. So design overstrings, without overstrings, this is a design without overstrings. Then the elastic one is this one, and design with overstrings, the blue one. So this is the difference. So all in all, this is the brief the description of response spectrum analysis and response spectrum analysis and response time history analysis, the differences, and the equation of motion, how to decouple the coupled equation of motion, how to decouple it, and the derivation of single degree of freedom system and multiple degree of freedom system, and this way, in this way. So when I come to our research, we discuss about classical modal analysis. You can view, this is the YouTube video, you can check it for the first video. So the second part of our discussion is response spectrum analysis. So response spectrum analysis part 2. This is the response spectrum analysis in the elastic buildings, 44 story and 100 story buildings. I analyzed it for our project, and this is a 44 story building, and I will show you all the 4 responses for shear, moment, and inter-story drift, and over all the responses as gathered. So RSA for 44. In the above section, we performed classical modal analysis for both sample RC buildings, and the natural period for 44 and 100 story buildings were 3.95 seconds and 9.94 seconds respectively. In addition to that, we have checked the overall health of our building. We found out that the first 2 modes are translational in the X direction and in the Y direction, and the third vibration was torsional in the Z direction as per code. Now we are ready for to perform RSA and time history analysis for both sample buildings separately, and we will compare the result for future recommendation. Ethiopian Standard 815 adheres to Eurocode 8 2004 regulations and previous study throughout this research. Therefore, the design response spectrum of ES 815 will be used. So, method of study for this research: a collection of standard 3-dimensional 3D reinforcement RC moment resisting frame made of 44 and 100 story multipurpose buildings are considered. Using the capacity design principle criteria in Ethiopian Seismic code ES 815 adheres to Eurocode 8 2004. The codes where we are going to use is the prescribed code as we discussed in the research objectives. Just to show you the Ethiopian building code, I already opened it here. This is Ethiopian building code. This is EN, Ethiopian Standard European Norm. This is the codes we adopted recently in 2015, and as per that code, for example, I also opened it, this one. This is a whole code, and I want to open this is PDF file for seismic design of buildings. I think I can close this one just to, we already complete this, so let me close it. the computer is becoming a little bit slower, so again let me close this. My laptop is a little bit slower. Okay, so as per Utopian code, I will come back here. Let me show you here the probabilistic seismic hazard zonation of Ethiopia. As per our code, this is ESEN 1998. This is European norm, the same as Euro code. So we have 5 zones. As per zone, this is zone 1, zone 0, 1, 2, 3, 4, 5. This is bedrock acceleration ratio alpha. As per this, the Addis Ababa, which is I am going to perform this building, it is zone 3. So we have 0.1. The PGA value 0.1 we are going to use for our analysis. I will come back this in a minute. And as per UBC 97 and IBC 2000, we are going to use S1 and SS values, but in UBC 97 we were using zoning and importance factor for determination of our seismic design. But I will come back in a minute here just to show you the Ethiopian building code. This is ESEN 1998-2005 Ethiopian standard based on Euro norm, design of structure for earthquake resistant part 1. So this is this was updated in 2015. Ministry of Construction was updated it. This is this committee. The committee was Haile Mikael Tafara, project coordinator Isaias Gabra Yohannes, he is doctor, he was my instructor. Technician committee also Adil Zakir, Fakadu Melese, Atalay Ayele, he is a professor now in Seismic City, Isaias Gabra Yohannes, Masala Haile, also all are doctors. And these people they already revised it. And just to read what it says, national forward, what they said: the proclamation to define the power and the duty of the executive organ of the Federal Democratic Republic of Ethiopia, proclamation number 691 2010, and Ethiopian building proclamation number 624 2009, empowers the Ministry of Construction to prepare the country's building code, issue standards for the design and construction works, and follow up and supervision the implementation of the same. The Ethiopian standard is the official English language version of the design of structures for earthquake resistance, ESEN 1998-1-2015. It spreads parts of design of structures for earthquake resistance, EBCS 8 1995, because in 1995 we have EBCS Ethiopian Building Code of Standard 8 in 1995, but now it is changed into the new version ESEN 1998-2015, which is withdrawn with an eye on the latest technology advancement and the trend worldwide, and with the aim of bringing the Ethiopian standard as per with the present state of the art. This edition has brought a major shift in terms of contents and comprehensiveness. Ethiopia is signatory member of CEN ELEC to adopt European standards in a similar fashion as the member and affiliates of CEN CNLEC. In effect, Ethiopia is bound to comply with these international regulations, which stipulates the condition for giving the basis framework of European standards, the state of the national standards, without any alteration. Even Ethiopia is a signatory. Even if we don't have our own code, because we are a signatory, we are forced to use also the European standard as per this. So I invite you to read the rest, but let me go to my, this is also Eurocore 2, design of concrete structure, design aided based on Eurocode. This is also the same. This is for concrete design aids. So we can see all the tables for column, beam, design. This is all. I can upload it in the YouTube video and we can see it later. Okay, let's go back to our presentation. So in this research, a collection of standard 3-dimensional 3D reinforced concrete moment resisting frame made up of 44 and 100-story multi-purpose buildings were developed using the capacity design principles and criteria given in Ethiopian Seismic Code ES 815 adheres to Eurocode 8/2004 regulations. This is method of study, geometric model, material strengths and gravity loads. Okay. We use the simple structural plan as shown in the figure 12 below. For the analysis model of the building in this research, a residential high-rising building, a plan layout of 45 by 36 and the central modal frames in transverse direction are used. According to Ethiopian ES 2015, virtually the same concrete and reinforcement steel strengths are considered for the design of beam and column cross sections. Concrete compressive strength 28 days C30 was assumed. Elastic modulus of elasticity, this one was used. Concrete unit weight also, reinforced steel and steel unit weight, all this parameter was used for our building. So lowercase definition, response spectrum, I will show you in a minute the response spectrum curve of Ethiopia. The response spectrum curve of Ethiopia, which is used in this, which was used for us, is let me go to page 36. I will show you. We have two type of response spectrum. Yes, shape of, this is elastic response spectrum. This is type 1. This is type 1 response spectrum for 5% damping as per Ethiopian Code of Standard. Horizontal elastic response spectrum. For the horizontal component of the seismic action, the elastic response spectrum is defined by the following expression. This is the expression. All the definition is here. Then this is prescribed. We simply follow. This is type 1. Again, to construct our once we know the ground type, and we can directly pick S, TB, TS, TD from this curve. So recommended type 2 elastic as per the intensity of the ground motion. This T1 and T2 are used. So for our case, define function response spectrum. This is a response spectrum I define, modify. As you can see, the ground acceleration 0.1. Then this one, spectrum type, we are using 1. Ground type, we are using B. Ground type B. A spectrum type, we are using 1. Soil factor 1.13. Then this spectrum period TB, TC, TD, lower bound and behavioral factors are directly picked from this table. this one. As you can see here, type 1. We choose type 1. So all TB, TC, TD for ground type B 1.35, TB 0.05, TC 0.23, and TD 1.2. This one, TD 1.2, TC 0.2, TB 0.05, soil factor S 1.35. Here 1.35, because the ground type we are going to use is B, and this is how we construct our elastic response spectrum for our research, because the T1 is for earthquake resistance greater than for earthquake hazard greater than 5.5. So this is how we construct our response spectrum. So as you can see, for different ground type, and we have different response spectrums. And again, I want to show you, for example, page 204, we have valuable information. Yeah, this is elastic displacement response spectrum, because if the time period is greater than 4 or 5 seconds, then we will have 9. For high rising buildings, we will have constant displacement, because this one is constant acceleration area, this is a constant velocity area, and this will be the constant displacement area after the long period time. So this is what we are using. TF will be with the ground type, but for ETAPS, once we give this property, it will directly calculate for us. It will calculate for us. Again, I have one thing I want to show you, page 22. This is, you see, probabilistic seismic hazard zonation of Ethiopia. So for the purpose of this standard, the country has been subdivided in accordance with figure D1. This is how Ethiopia is divided. D1 and D2 and D1, D2 and table D2 is seismic zone, depending on the local hazard. The hazard map is primarily and is processed from instrumentally recorded as earthquake catalog. As per my first video, I tried to show that the seismic map of Ethiopia needs to be revised, because the first map of Ethiopia was developed by the Canadian guy. His name was Goanin, but his seismic map, the first seismic map, was not perfect. There was some amendment, then 2 revisions until now was done. So now we are in the 3rd revision of seismic code of the country, but still there needs to be done a lot of extensive researches in the country. So as per this, bedrock acceleration is this one, zone 1, 2, 3, 4, 5 is this one. So as per Addis Ababa, we have 0.1, alpha factor will be 0.1. so in our ETAPS we will put alpha here, ground acceleration, AG over G, 0.1 will be here, soil factor will be 1.35, spectrum period 0.05, spectrum period TC 0.25, spectrum period TD 1.2, lower bound factor 0.1, and behavioral factor Q. This is elastic response spectrum. For the, I didn't use any behavioral factor here, just to know the elastic response spectrum. The inelastic response spectrum will be considered later. Okay, let's go to our presentation. 240, just to show you the country's division. This is the region, this is town, this is longitude, this is latitude, this is seismic zone. So the country is divided into different seismic zone as per the seismic map of the Ethiopia. But as per the code, starting from IBC 2000, the country no more, most countries no more they are using any zoning, but they are using SS and S1 values, spectral acceleration and spectral displacement, for the seismic design of their structure. So that is what performance based is. This is all the regions in Ethiopia, Tigray, Amara, Tigray, SNMP, Afar, Oromo, all these are divided into zone 1, 2, 3 until zone 5 as per the peak ground acceleration zonation and the country map, zoning map calculation. Okay, so this is the floor map of our building. This is a model, as I showed you, around 45 times 36. This is the shape. Adhere to Eurocode 8 2004, we already discussed now. This is a material property I'm going to use, and everything we discuss now, you can read it later. Everything is included. Then finally, the floor loads are transferred to the model frames, floor beams, in addition to seismic mass combination. Okay, as per the code, the floor loads are transferred to the model frames, floor beams. In addition, for the seismic mass computation, the program considers 30% of the live load in ES 815 adheres to Eurocode 8 2004 regulation correspondingly, in addition to the dead load for dynamic study of the frames. This is very important part. Design spectrum, input design response spectrum, I already showed you, but just for the sake of demonstration, the code considers multiple seismic design hazard levels of ground motions in its design response spectrum for seismic design. The Utopian seismic code ES 815 adheres to Eurocode 8 2004 regulations, divide ground motion into two categories. In the first example, the reference ground motion is associated with 10% of likelihood of exceedance in 50 years. This is around 475 years return period. Therefore, no local or global collapse of structure is allowed in this level. No collapse requirement, which refers to the ultimate limit state. That is what we call it. The other has 10% of chance of exceedance, exceeding the limit in 10 years or in 95 years return period. But unfortunately, this one was removed from Utopian building code once the new code was adopted. Buildings are built to have a sufficient resistance and stiffness to preserve the function of critical service without causing damage. Therefore, the corresponding constraints in use refers to the design limit. For non-collapse requirement, the reference peak ground acceleration PGA map is used to classify Utopian seismic into 5 zones. Zone 1, 2, 3, 4, 5, 6. This is the GPA, GPA value 0.04 for zone 1, zone 2 0.07G, zone 3 0.10G, 4 0.15G, 5 0.2G. The damage restriction is 0.4 to 0.5G times the non-collapse requirement. The 10% exceedance in 50 years provided in the code is used in this investigation. For 75 return period is used in this investigation. The code defines their response spectrum, which contains various parameters based on the seismic design hazard levels. Okay. So ES 815 adheres to Eurocode 8 2004 regulation response spectrum. The code was described using a single parameter PGA of two type of response spectrum. Type 1 used in this study has intensity M greater than 5.5, and type 2 modest intensity M less than 5.5. For various soil type, the reaction spectrum is specified with corner times TB, TC, TD, as I have showed you already, and defined up to T 4 seconds, the time period until 4 seconds. But for the longer period, which is in our design response spectrum, for the longer period, we will call it the constant displacement period. We will use the other formula, but ETAPS directly calculate that. But we are going to use type 1 code. So this is our response spectrum design. This is design response spectrum. Elastic response spectrum also. This is also inelastic. When it is inelastic, that means we use the code factors, over strength factors, R factors, CD factors, I factors are considered. This is for inelastic response spectrum. As I showed you, this is a table for TD, TC calculation. Once we know the ground type and the type of type 1 response spectrum, elastic response spectrum, then we can use this. If we were to use the second type of response spectrum, then this was the table. So whereas the Ethiopian code adheres to Eurocode, this regulation divide the country in this one I already discussed already. So the soil type will be this one, and the velocity V30 value will be 360 ms, and 800 meter per second was used in this study. In Ethiopia, PGA is calculated using the peak ground type A. In this study, 0.1 G Addis Ababa Zone 3 in US is employed in model building design. Furthermore, the code uses the response spectrum in various methods to estimate the model structural design seismic input loads. This is also I have showed you now. Just in addition to the elastic response spectrum, the Ethiopian code uses the design response spectrum, also known as inelastic response spectrum. It is calculated by altering the elastic spectrum of a structure for elastic analysis by ductility and behavioral factor Q, and accounting for nonlinear effect utilized in the design of structural member sections. The capacity of structural system withstand nonlinear seismic activity is measured by the behavioral factor. This one also I try to show you in the mathematical formulation of single degree of freedom and multiple degree of freedom system. We saw it what response spectrum, what R factor is, CD factor is, omega factor, and everything was discussed there. Elastic response spectrum, this is what 5.85. This will be for design response spectrum. So as per this is the response spectrum of Ethiopia. All the things are taken from the code, and we use ETABS 19 version for the analysis, and the ground excitement in the horizontal direction subjected to modal response spectrum analysis, RSA. So I will show you in a moment. This is the result. So let me go here. So after we define the response spectrum and as per Ethiopian code type 1, then I use the response spectrum for load cases. So here response spectrum SRSL. So if you modify, as you can see, I apply in both direction, X and Y direction. This is a response spectrum. The modal shape I am going to use is from modal, and the mode combination is SRSS, and the damping is 0.05. SRSS is the type we are going to use, and so the result, everything is the same. Material property, this steel, concrete, diaphragms, section properties, wall sections, everything is all the same. P delta analysis, mass source, the mass source is also defined. This is a mass source. We are going to take 25% of live load. SDL is 1, dead load is 1. This is the mass source we are going to consider, and in lateral include lateral mass, and lamp lateral mass as story level are checked in. And the other thing which I will show you is only this is a basic one, response spectra, Ethiopian spectrum, and the result display response plots. The response plots, as you can see, this is maximum story displacement, dead load. No, the load type we are going to choose is response spectrum, this one RSL response spectrum. So as per this maximum story displacement, as you can see, this is our maximum displacement in the x and y direction for 1 millimeter, and we can change this one, story drift, the percentage of story drift. As you can see, almost 0.4% is the story drift, and shear force, story shear, this is the story shear. Again, a story moment, this is a story moment. In this way we can see the response of the structure in the global level, the global response of the structure, the moment, everything is here. Then in my analysis, in my research, I will incorporate the result. This is the absolute lateral loads, as you can see. This is absolute lateral load to diaphragm. We will use this for pushover analysis later. So load pattern is earthquake x, and this is in the y. Again, autolateral load in the y. Diaphragm, this is the diaphragm, this is the drift ratio. So this is the results. So this is our second video. The first video was in the classical modal analysis, and this is the response history analysis. So the results will be compared. The third video will be time response analysis, but here figure 15 depicts the design spectrum for horizontal direction. The square root of sum of square SRSA rule, SRSS rule was utilized for the combination of distinct model responses as recommended by ES 815. The modal frame RSA model analysis result as per RSA X, as I showed you. Global response, lower cases was maximum story displacement was 420, maximum story drift was 0.4%, story shear was 60,898 kilonewton, and story overturning moment was found 3.74928 times 10 raised to 6 kilonewton per meter, and their corresponding graphs are shown in the figure, and I have showed you also in the ETAPS. The figure depicts the modal shapes, even the mode shapes, and everything was as per the code. This is the results as I showed you. This is first mode, this is second mode, this is first mode, this is story drift, and the same. So this is the result. The mode 1, we have 20 modes, and this is a period, and this is a frequency. As you can see, when the modes are increasing, the frequency increasing, and the frequency will increase. I will show you in a moment also. Mode shape and mass participation coefficient, as you can see, the first mode is, the period is 3.806, and the modal participation factor 71.87% of the mass was in the pure x direction, and mode 2 was 3.585 seconds, and it was 72.74 mass of the building was participated in the y direction, and the third one is pure translation, rotation, 71.87% of the mass was recorded. So you can go in this way to see the result. So this is the overall output of the response spectrum analysis. We can find in the x and the y, because I defined in the x and the y both response spectrum, Utopian building code, as per Utopian building code, type 1 response spectrum. So this is maximum story displacement 421.9, maximum inter-story drift is 0.4%, a story shear is this much, around 60,898 kilometers, story overturning moment are this one. So in this way, the same thing is true for 100 story also. I have 100 story, the result is this. And just to show you the output, maximum story displacement 4314.25144 millimeter. Maximum inter-story drift was 1.72%. A story shear was 98.5137. A story overturning moment was 18.645 times 10 raised to 6 kilometer per meter square. This is no need. So response spectrum analysis, this was so just to show you the I have video also, but to show you the combined this one, story response, and if you want to see, for example, because it will take time, but I will show you the combined response. I think I have the video. This is the response spectrum 44 output. No, I don't have, or I have, I don't know. Okay, so this is supporting documents. Okay, so just to wrap up what we did, we as per my research questions, I have to conduct 5 analyses: classical modal analysis, response tree analysis, time history analysis in the linear models, and after this video, the third video will be in the linear time history analysis. Then the 4 global response of the structures will be compared: the fundamental time period, the frequencies, the shear, moment, story drift, and everything will be compared each other for 44 and 100 story buildings. And after that, we will change the model into non-linear model with plastic engine modeling. And for shear forces, we are going to use fiber modeling approach. After that, we will conduct pushover analysis and non-linear time history analysis to verify the results and to check the outputs. That's what we are going to do. And in this video, we saw what is the response spectrum, the mathematical formulation of response spectrum, and the derivation of the equation, and the uncoupled equation of motion, and how we decouple it with q coordinates using mode shapes, and multiply with q coordinate and take the result into u coordinates. And by doing so, we decouple the equation of motion for each mode differently. And if we are finding the response of a structure by calculating each response, each equation of motion, and for each modes, and sum the result, the analysis type called response history analysis. But if we use single degree of freedom system with for a constant damping ratio and for a fixed time, and if we run our system, and if we pick the maximum displacement and run our system for different time period, and construct our displacement response spectrum, and we drive pseudo velocity response spectrum and pseudo acceleration response spectrum from our displacement response spectrum by multiplying omega for the pseudo velocity response spectrum, and for pseudo acceleration spectrum we multiply it with omega square, and we can simply find our response spectrum for our site. And simply for any structure we have, once we know the time period, and simply we go and take all the available responses of the structure, and we will finally we try to see also response spectrum is pseudo response spectrum dynamic analysis, because it is not static and it's not dynamic, because the only thing once we generate the displacement response spectrum with modal shape times 3 omega and everything, then everything will be like equal to analysis. So once we have A, the pseudo acceleration, we will multiply it with W, then we will find the base shear acceleration. So M over G, A over G, we call it the base shear coefficient, many codes. And in addition to that, we try to see the UBC code-based response spectrum and IBC 2000, and we try to see the modal participation factor should be 90% and other things. And at the end of the day, for our project, for our research, I make analysis for with Ethiopian building code of standard, and I define the response spectrum of Ethiopia as per type 1 and soil type B and the gravity 0.1 GPa condition, and we found the global responses for comparison. So next video we will see a response time history analysis, and we will discuss what we need in detail. I really appreciate. Thank you so much.